Hi everyone, let's go over the worksheet in a more organized fashion, and hopefully this will help you understand combustion analysis. Two different types of combustion analysis, and remember, we're trying to find the subscripts on our compound. So basically we're using combustion analysis to find the empirical formula. The first kind only has carbon and hydrogen, okay? I just find my mass or my moles, divide by lowest, then make whole. That is the amount of carbon. Well, after we burn all this off, we're going to make carbon dioxide. All the carbon that comes from the carbon dioxide came from the carbon that we burned. So whatever mass this is has to be the mass from here. Why? Well, that is your law of matter and mass, conservation of matter and mass, right? Can't be created nor destroyed. Here we have hydrogen, or only hydrogens here. So when we're all done with our reaction, all the hydrogen that's here came from the hydrogen here. So when we figure out the mass or the moles of hydrogen here, it has to be the mass or the moles of hydrogen there, okay? Then we come to our second type of combustion analysis problem, and this is carbon, hydrogen, and oxygen. So it's a hydrocarbon with oxygen in it. And this is very similar. All the carbon here has to come out here. So the mass or moles of this, same with our hydrogen. However, that's very different with our oxygen. Why? Because we have oxygen in two places here, and we have oxygen in two places here. When we're done with our combustion, some of it came from the oxygen reactant and some of it came from the hydrocarbon that we are burning. So in order to find how much oxygen is here, we have to find the actual mass of the carbon, the actual mass of the hydrogen, and subtract it from the total mass of our sample, right? So what we have left is the mass of the oxygen. Remember, we can't just add up these two oxygens because some came from our hydrocarbon and some came from our oxygen that we used as our reactant, okay? In order to do problem number 2, we definitely need the total mass of the sample so we can do that subtraction. There are several ways to do this problem, and if you look it up on the internet, you'll see multiple ways. I'm going to use the quickest and easiest way. However, finding the mass of one element using percent composition might seem more straightforward to you than finding the moles, okay? So we've already done that. We add up, get the total molar mass. 12 grams is the molar mass of the carbon that came from carbon dioxide divided by the total, part over whole times 100. We get 27.289%, and here we get 52.261% of oxygen when I take my oxygen divided by the total molar mass, and that becomes 52%. If I use these numbers and multiply it by the mass of a sample, then I can get the actual grams that are in carbon dioxide, okay? If I do it with water, here's how you do the percent composition of water. If I multiply that by the mass of water, I can find the mass of the total amount of hydrogen, or the mass. A little out of order, but we did talk about rounding. When we get our mole ratios, we divide by lowest, and then you might have numbers that come out like this. Okay, 1.25 is basically 1 1/4. And so 1 1/4, if we multiply by 4 to get rid of our denominator, we will make that whole. 1 1/2 is 1 and 1 1.75, that's 3/4 multiplied by 4 to make it whole. And then we're looking for our thirds and our 2/3, and both of those are multiplied by 3. And everything else, don't worry about, okay? We're not going to get that complicated here. That's as complicated as we're going to get. So now, on the worksheet that I tried to work on with you today, I am going to do model number 3. We are looking for our carbon, hydrogen, and oxygen. The total mass of this sample is 10.00 grams. We will combust that with oxygen. We will make carbon dioxide, and when we do, we get 21.96 grams of carbon dioxide, and we also make 11.99 grams of water. What are we looking for? These problems get complicated. There's a lot of steps, so make sure that you know what you're looking for. So we are looking for these subscripts. What is the empirical formula? In order to do that, we can use this chart. Okay, don't put in this yet. We'll get there. And we can find grams right away, or we can find moles. Remember, if we're going to find grams, I can multiply of carbon and my percent composition of oxygen. Right here you can see if I multiply 11.99 by 11.21, that would give me my percent hydrogen in this sample, and I would start with grams, okay? And then you can convert that to moles. That's a perfectly fine way to do it. If we do it where we go from find the carbon and hydrogen grams, so we can subtract it from our 10 grams and figure out the mass of oxygen. Okay, so let's just start with the moles. How do we find the moles of carbon? Well, we had 21.96 grams of carbon dioxide. So if I get rid of my grams and goes to moles, dioxide. When we do these problems, it's important to keep as many sig figs as you possibly can. And since they gave us this number and we multiplied, we have 4 significant digits there, 4 significant digits there. I'm going to keep 4 significant digits. Okay? Now, once I have 0.4990 moles of carbon, I need to look at carbon dioxide. Okay? In carbon dioxide, I have 1 carbon, I have 2 oxygens. But I have 1 mole of carbon and 2 moles of oxygen, right? So I can notice that for every 1 mole of this carbon dioxide, I have only 1 mole of carbon. The number would be the same. If I'm going to set it up with ratios, here's my carbon dioxide. For every 1 mole of carbon dioxide, I have 1 mole of carbon. I get the same number. I also want to show you this in one whole string, right? I'm getting rid of that. I'm going to moles of carbon dioxide. I get rid of moles of carbon dioxide. I'm going to moles. I did the same thing here with hydrogen. I converted it into moles of hydrogen, and then my mole ratio for every 1 mole of water, I have 2 moles of hydrogen. So then I get 1.311 moles of hydrogen. So going back to our chart that we need to fill in, I've put hydrogen. The last thing I need to do is fill in my oxygen. How am I going to get that? So finding my mass of oxygen. So in order to do that, I need to find my mass of carbon, okay, and I can do 2 things. I already have moles, so I'm just going to figure out how many grams that is. I get rid of moles, I go to grams, that's my molar mass from the periodic table, and I get 5.993 grams of carbon. Okay, remember you can do it with mass percent, or you can just change the moles that we already found into grams. Mass. 344 grams of hydrogen. Now, here is my formula. In this whole formula, I burnt it. That's my combustion analysis, and I burned 10 grams of it. If 5.993 grams are carbon and 1.344 grams are hydrogen, all the rest must be oxygen. So I just subtract. Okay, and so I can put that in my chart, which is 2.66 grams of oxygen. Now, because I've subtracted and the number that we started with went to the hundredths place, that's my least precise, so my answer should only go to the hundredths place. Okay, so that's what I did. I went to the hundredths. And now, I didn't, because when you go to combustion analysis, the more numbers you have out there, the better it works. But in any case, I took my grams of oxygen, 2.66 grams of oxygen, and I converted it to moles of oxygen. So now I have my moles of oxygen. The last step we have to do is to get that whole number mole ratio. I can't put in carbon 0.499, hydrogen 1.33, and oxygen 1.66, right? I can't do this. Faster, oxygen 0.166. That's not a formula that we can use, right? We don't do that. I need a whole number. Fastest way to go from 1 and up is to divide by my lowest number, and I get 1, 8, and 3. These are already whole numbers, so we're good. My oxygen 1, we don't put the 1 there. Okay, so hopefully this was a clear way of looking at this problem. Take notes on it, and we are going to be moving on to more problems like this and some including hydrates.